We also work with the census, but these are our own views. This work was largely independent of our census work, but inspired by some of our efforts. So I want to focus on a class of problems that I'm going to call assignment problems, which involve a disjoint set of assignee populations. And in this talk, there are basically always going to be groups of people that live in geographic regions. And these problems have to do with assigning like benefits or privileges to these groups of people that depend, and the decision to grant those benefits and privileges depends on statistics about those groups. Okay, so in the absence of privacy or noise or anything, we have a bunch of disjoint groups. We can compute some statistics on them, and then we run some kind of assignment method to generate outcomes, one for each group. A simple example of an assignment method might be a Boolean outcome that happens for an assignee population if some property of that population is greater than a threshold and doesn't happen otherwise. Another example might be proportional allocation, where we have an entitlement of money and we're going to distribute it in proportion to some qualifying population in each region. Okay, so there's lots of really important problems that fit this format. Federal funds allocation, the assignee populations are states or counties or school districts, and funds may be allocated to population counts, not necessarily the total population, but population of some segment of the group. Congressional apportionment, of course, is a really important problem where states are granted seats in the House of Representatives, and it's determined by resident counts. I'm going to talk about an example later in some detail that is federal funds allocation, and I'm going to talk about minority language voting rights benefits, which are granted, so certain voting jurisdictions are covered or not covered, and it's determined by a certain set of statistics on the population and their literacy and how many people speak foreign languages. So, and there's other examples that, so now when we're going to move into like how to do these assignment problems privately, we have to cope with the risk of mistakes being made. And so the mistakes here are, serious consequences in some cases. Federal funds can be misallocated, seats in the House can be misallocated, and we have unfair representation. Minority language voters can be disenfranchised if they don't get the benefit of voting materials published in their language, and so on. So we expect that we have to deal with some of these consequences, and we can think about, it's a natural social goal to try to minimize in aggregate how much money is misallocated due to errors in the data that we publish. So we'll get to that, and part in the big point of this talk is to think not just about overall error and misallocation in these problems, but also disparities and whether different groups are treated differently as a byproduct of privacy mechanisms. That's where I'm headed. But before I get there, I want to talk about some different settings for how we might do private assignment. So this is like the setting I showed you on the first slide. This is like non-private assignment. The most natural approach, and one that's close to what the census does, is data publication with sort of standard assignment. What I mean by that is that these assignee populations will compute privately the supporting statistics about them, so we'll get noisy statistics out. We then just run the assignment mechanism kind of as if they're true. These statistics are true. And we get noisy outcomes. Slightly different approach would be sort of data publication. So we release the privately computed statistics, but we could change the assignment function because now there's noise. And we should maybe do something a little bit smarter. We still get noisy assignments out, outcomes out. And then, of course, we could forego publication completely and do direct kind of differentially private assignment and just go from compute the noisy outcomes directly. We might be able to do better in this setting, a little bit better, but there are some issues. And so this talk is really going to focus on this first setting, which is the simplest. And the reason for that is that this is sort of preliminary work we're just starting to think about, and we haven't gotten to the other settings yet, but also there's some significant challenges to moving here. Okay, first of all, you have to change the assignment function. And if you want to do that intelligently, you need to know something about the noise, and that information is not always available. Second of all, these assignment functions are often encoded in law or regulation. It's not clear, at least to me, that they can always be changed. And I think the biggest problem with this approach is really that there's no transparency. So, I mean, a lot of these critical problems rely on people being able to check the outcomes to some extent and trust them. And I'm not sure we have that if we go with pure private assignment. Okay, so now issues with data quality are not a new thing for the census, and errors in these types of assignment problems have been carefully considered. But I want to point out that, you know, even though, for example, census tables that are based on surveys include estimates of sampling error, those estimates and other estimates of error that come with census published data generally do not reflect the impact of disclosure limitation. Okay? So we can't take that into account easily in these assignment problems. What the census will do for really important assignment problems is take special efforts to make sure that assignment happens accurately. For redistricting and apportionment, there are some supporting statistics that will not undergo disclosure limitation at all. For voting rights determinations, there are special variance reduction methods to deal with the fact that the counts are really small and sampling error can be high. Okay, so, but in general, the published tables are treated as true for assignment problems, and there's some critical assignment problems that the census is sort of like very closely involved in, but there's also, for sure, lots of assignment problems that are carried out using census data that the Census Bureau knows nothing about because the statistics are published and used all over the place. Okay, so we have these important problems, and we have privacy mechanisms, and we're moving towards differentially private mechanisms. And so we've seen this graph, or versions of this graph, a few times this week. This is a paper that's a really nice paper by John and Ian that motivated, you know, our further thinking about this problem. And I'll just remind people who might not have seen it that this is the sort of best favored outcome, where accuracy is maximized and privacy loss is minimized. And that this dark line is the prediction frontier of sort of non-dominated solutions, and that if you know how you want to exchange privacy loss and accuracy, then you can pick an optimal point. So I want to point out that in their paper and in a lot of mechanisms, the accuracy measure here is an aggregate error, total error, and that corresponds to a utilitarian social welfare in which what's good about accuracy is sort of like the sum of all the accuracy that everybody gets. And that's a different social welfare function than others that would think carefully about, for example, how the worst person is doing and whether some people are disadvantaged relative to others. So that's what I want to talk about is accuracy disparity. Even if we fix a privacy loss budget that's acceptable, and we pick the best available mechanism from the plot we had on the previous slide, do assignee populations bear the burden of inaccuracy equally or fairly? So we might find that, you know, if we were classifying our counties in Texas, that some almost always get classified correctly, but others are really disadvantaged by the fact that they are very rarely classified correctly. So I want to show you a different plot, which is a sort of a different social choice that I think we have to make, which is about overall aggregate accuracy versus disparities across the groups that are receiving outcomes. And this is maximum accuracy. So presumably on the previous slide, you know, for whatever fixed epsilons, this is sort of like another dimension, but I picked an epsilon here. So I have on this plot the best mechanism, the most accurate mechanism for that accuracy level. But here what I'm saying is that, you know, I could pick that but maximize accuracy, but I'm going to show you some examples where that means that I will also create disparities. And that if I want to reduce the disparities, I will have to sacrifice some overall accuracy. Yeah, question?
I guess I was just going to ask
This is not like a real graph. It's like a
Just like, is that, I mean, I could imagine lots of situations where the relationship is more positively correlated, right? So
well,
do you have a sense of how?
I'm going to give you a few different specific scenarios where this phenomenon arises from common mechanisms. Yeah.
Some of this, I think, probably comes down to how you define accuracy disparity. But I mean, if you imagine going to the very bottom of this line, where you say we have zero accuracy, we're just going to make a constant decision. Right. What is the accuracy disparity in that case?
Yeah. Well. Okay.
Is it high because?
Yeah. Yeah.
Decision every time for a certain subset?
No, I think, yeah. I mean, I think in that case, I mean, I think this is limited to a specific mechanism for a specific epsilon in the plots that I'm going to make. And I think, I understand where you're going with that question, I think, but there should be you should somehow get back to fair and no disparity if things get really bad, but yeah. Okay, so in the remainder of the talk, I want to try to give you specific examples, like I said, of where these disparities can arise. And then those will be sort of like, just sort of like simple applications of existing mechanisms. And I think it won't answer the question of whether these problems are real in practice. And so then we're going to do some case studies and try to see what the impacts look like for like reasonable epsilons. Okay, so what are the things that can arise in mechanisms? Different groups that are assignee populations can have unequal error rates in the counts that are estimated from them, right? That just means that, like even if they're unbiased, they can have different variance. And so one of the aspects here is that these assignment problems are not rerun very frequently. It's not that we do apportionment, every hour. And so that the repeated random trials things sort of like even out. We do these assignments often like annually or every 5 years. And so if you get a bad coin flip, you have to live with it, okay? So unequal error rates matter, and bias in estimated counts, and also unequal outcomes. So these are like properties that we observed about the error coming out of the mechanism, but you can also kind of measure things in the outcome space and see whether, and that's a little bit different. And I don't think we're sure exactly where to measure these effects and what the right metrics are, but I'm going to show you what creates these effects. And so post-processing can create bias. Data adaptive algorithms lead to bias. I'll show you examples which are very common, where we optimize total error on a workload and we get unequal error rates across a population. And then I'll show you an example of like a threshold condition and how in the outcome space, even if you have very sort of like fair error distribution, you get weird effects.
Can I just make a comment?
Yes.
I believe they all apply to sample-based survey measures that are used the same way. And comparisons with orders of magnitude in such surveys are reasonable things to do here.
So you mean if we can claim that our mechanisms produce effects that are sort of smaller than those effects, we'd be in good shape, or?
I mean that post-processing deliberately reduces bias in the language determinations in order to control mean squared error. Adaptive algorithms in that context are ones that examine the space of actual districts and actual languages to attempt to minimize the discrepancies between the various ways that the parameters in the post-processing can be tuned. I'm really trying
but
we're actually addressing a generic problem here, and we focused on the privacy mechanisms, but the Census Bureau has to use sample-based surveys to do this all the time, not just in the ones you highlighted.
Okay.
Housing-driven development takes the block group tabulations from the American Community Survey and makes housing subsidy determinations on them, and then complains the next year when the next 5-year one, because of sampling variability, has these things moving all over the place.
Okay, so I thank you for pointing that out. So these problems exist independent of our privacy mechanisms. I think the point of this work is to try to understand how are we creating new effects in our privacy mechanisms? And I guess eventually we have to understand how they compose with sampling-based effects.
Actually, I'm going slightly more general than that. You're trying to address a class of problems that already exist in the use of statistical data for making especially zero-sum allocation problems, where there are winners and losers because it's a fixed pie.
Okay.
Possibly not focusing so much on the fact that they're privacy-preserving algorithms that generate these outcomes, but focusing on generic features of data processing that then have to use noisy measures to make zero-sum allocations is a more general problem. And you could talk about it without singling out the privacy mechanisms.
Okay.
I have a selfish reason for doing this. Singling out the privacy mechanisms makes them look like they're the culprit here, when really many of the things that we do that induce noise in data should be treated as the reasons why the data are imperfect measures on the thing you're trying to do allocations of. The poverty measures, which have very limited disclosure requirements, have been subjected to this kind of scrutiny for decades.
John, let me
Okay.
jump to your defense here. We talked about that yesterday, and the thing where it's interesting is it could be that because of the privacy mechanism, some of these other errors are actually less. You can reduce some of them, right? And so I think Gerome was very well aware that this is there, but the question is sort of to where do you amplify, and where could you even reduce the problem that's there already? And that's, I think, an interesting question.
Yeah.
Okay. And I think another key thing coming out of this is there's a lot of work already done. There's languages people use to talk about this, and to the extent that this can fit into that same framework and language, I think it buys us a lot in terms of, as John points out, saying that that this isn't a new problem. It's not a problem we've introduced. It's
Okay.
an aspect of it. So,
All right, well, let me try to go on. I mean, I certainly need to learn more about that language and that history of work, because it's not my area, but what I understand is privacy algorithms, and I want to understand where they create these effects and how they compare.
I interrupted you here, not so much because I think that you don't know this, but because I wanted the audience to be generally aware that these are generic problems associated with the use of statistical data for public decision-making and allocation.
Okay. All right. Let me go on. Okay, so I'm going to walk through some mechanisms, basic mechanisms. We're going to start with the basic things. Here's some true data. It's a histogram. Imagine that each bucket here is one of these populations, and that we're reporting a count about that population in order to make a decision. Okay? If I apply the Laplace mechanism, then what I'm showing you here is literally over many trials. This is a little box plot which describes the distribution of noise that each population is going to experience. And so you see that it's like unbiased noise, and it's got equal sort of variance. This isn't exactly plotting variance, but it's got equal variance as we expect for the Laplace mechanism. What people often do, a simple method for computing a histogram with Laplace noise, then you realize that there are negative values, and you do some kind of normalized rounding. And as soon as you do that even simple type of post-processing, you get noise distributions that are a little bit skewed. Okay, so you see some bias, you see some unequal variance happening here. Okay. Another class of mechanisms that's practically important are data adaptive mechanisms. These mechanisms are actually exploiting properties of the input data, typically to lower variance, but they create bias. Okay, so the DAWA algorithm, this is one of our algorithms, does a kind of like data reduction step where it privately looks for adjacent sets of bins that could be approximated better by just taking a kind of total count and then assuming uniformity, because you kind of don't have enough signal to distinguish these bins anyway, and you might as well take a count and assume uniformity. So what's shown here is like grouping this histogram into groups, and then this noisy estimate is uniform in all these regions. That creates a kind of bias, but it actually can lower squared error, lower variance a lot. The multiplicative weights mechanism starts with a uniform estimate and iteratively improves it by selecting the least well-approximated query privately, and then measuring it with Laplace noise and doing multiplicative weights inference. Okay, so if we go back to look at the results and we see this is sort of like Laplace noise, nicely regular. This is the DAWA algorithm. This is MWM. Okay, I'll show you again the original distribution. So we see now the sort of the question for the algorithm designers is, can we explain what's going on here? Because there's big deviations. You see people with unequal variance. We see this sort of negatively biased, massive, variation here. What's also interesting is that we've lowered a measure of total error. So DAWA is delivering better total error, but creating a kind of disparities. Okay. So if I went back to that plot, I could plot this and say, well, Laplace has like lower disparity, but not as much accuracy as DAWA. All right, so now I'm going to give you another example. A lot of times, a very frequent case is that somebody gives us a workload. This is, I talked about this mechanism in the boot camp a month ago. We optimize to find a strategy that helps us answer the workload queries with low error. The workload is usually input from users that say, this is the thing I want to know about. And we select a good strategy, we apply the Laplace noise to it, and we reconstruct the answers. A good strategy is one that is lower sensitivity than the workload, but can support accurate reconstruction. It's got some nice properties. The answers to the workload queries are always unbiased, so we're not creating bias here. It's got data-independent expected error rates, which are handy. But it will create expected error that sort of varies across the workload. Okay? So I wanted to show an example of kind of a case where you might use such a mechanism is a kind of geographic hierarchy where you have counties and states and the nation. And you want to count some predicate. It could be total population, but it could also be the number of needy students in counties. And you want numbers for each county, for each state, and for the nation. Okay? So the matrix mechanism can optimize this workload, and what it'll try to do is find a set of measurements from which all of those workload queries can be estimated, and the total error will be minimized. So we don't always, I think it's not always necessarily the case that we expect all workload queries to have the same expected error. But we might look at the sort of states and ask, well, would these counts coming out of at least this state level have roughly equivalent error? And what we find here I've gone right to the sort of chart of accuracy disparity versus total accuracy. And these are different sort of solutions, different strategies that could be used to answer the geographic hierarchy. We find that HDMM, our implementation of the matrix mechanism, will improve on, we'll find the most accurate solution, but create some disparity compared with, for example, other solutions that answer the workload queries themselves and then do inference. I can talk more about the details of this, but you get sort of like populations across states that are quite skewed and somewhat arbitrary. I think this is Virginia, and I'm not exactly sure why. But we're using an optimizer. There's part of the challenge here is that there's a lot of skew, if you didn't catch it, in the number of counties per state. Some states have 3 counties and some have 250. And what the matrix mechanism is doing is an inference process where it uses the noisy counts at the county level to improve the state population counts and the national, so you start to see these artifacts.
Jerome?
Yeah.
You're using the measure of disparity.
Yeah, so here the disparity measure was sort of like the maximum expected error minus the minimum normalized by the average.
So, but in general, do the use cases that you mentioned have agreed upon measures of disparity?
No, I don't think so. We're trying to, we've considered a few. In the write-up on this, we have a few measures. And in the case studies, we'll see other ones. Yeah, but I'm not sure, what exactly the right measure is.
So maybe also a question to John, like if one wants to design algorithms that have better accuracy disparity. That's one of the parameters of the algorithm, of a good algorithm. What would be good measures to shoot for?
Remember this first slide where you said there's different social welfare functions that you can use here? You have to say, do you want the performance to be good on average? Do you want the performance to pull the bottom of the distribution up with high reliability? Do you want the performance to pull the top of the income distribution down with high reliability? If you don't specify the objective, then you can't tune the accuracy measure to accomplish it.
No, of course. What I was asking is whether there are agreed upon measures that we could shoot for when we design algorithms for this stuff.
Possible allocation problem you can imagine. The seats in the House of Representatives, they argued about it for 2 centuries and then just wrote a formula into the statute because the Constitution was consistently interpreted as requiring first past the gate majority voting, and so it just needed to hand out the seats. You can't switch it over to proportional representation or pair voting or rank voting. So I don't think there's an easy answer to that question. The statutes, the clearest statutes, write all of the rules down, and then they designate who gets to make the decision, and they prohibit judicial review of it. So that basically chips in stone that this is the way it's going to work, and then you tune everything to that. That's the best answer I can give. It's probably not good.
Yeah, I mean, as we saw in an earlier talk, I mean, in some things it may be getting the count right matters, but in other things, all that matters is the rank. You could get, your counts may be half what they should be in some and twice what they are in others, but if you get the rank right and people are applying all their resources to whoever's at the bottom, then...
Most of the ones in the federal government that I know of that we do statistics on at the Census Bureau, if you got the proportion of the population right, you would not affect the allocation.
So it's, it's so dependent on how it's being used.
Yeah, so it may be problem specific, but that creates its own challenges for a scenario where we're publishing a reference set of statistics and expecting everybody to use it for these assignment problems. Ashwin, did you want to add?
Just to add on to that, I think disparity in sort of accuracy or disparity in sort of treatment is very problem specific. Just like we know in sort of the machine learning literature, even in like the allocation or the participatory budgeting kind of scenarios, there are different kinds of measures that people try to optimize for MEP-ness and core and so on. And so they all give sort of slightly different objectives that you could optimize to.
Okay, let me try to go on. So let's no, I appreciate the questions. And this has been a great discussion. So let's go back to a scenario where we just use Laplace noise. So we don't have any disparities in, and we don't have any bias, we don't have any disparities in error rates, but we are going to do something with this data, which is test who's above a threshold. Okay, so we want to isolate the assignment populations that are above 25, and if we do that with Laplace noise, we already see a lot of disparities, right? And this basically maps exactly to how close to the decision boundary is the true data. Those people are much more susceptible to this, even the same amount of noise. Now we could even consider a scenario which again gave better total error but creates greater disparities. And again, we see that there's this accuracy disparity trade-off. Okay, so now I'm going to go on to the case studies, and I mean the same effects are going to appear, but I guess the advantage of this is that these are real problems on somewhat real data, and we can ask the further question, which is like, well, at the epsilon that I care about, are these effects really going to matter? So the first problem that we're going to talk about is the minority language voting benefits. So this is part of the 1965 Voting Rights Act. It's Section 203. It states specific conditions under which a jurisdiction, which is like a small voting district, will be covered for a specific language, one of 68 languages, I think, considered separately, and each jurisdiction can be covered or not covered. And if they are determined to be covered by the Census Bureau, they have to publish all the materials in the minority language. These determinations are made every 5 years, and the data is made public. And so, for example, it's a fairly rare classification. So, there's 8,000 jurisdictions, and in 2016, 263 of those jurisdictions were covered for some language, at least one language. But it ends up being a significant fraction of the population that's potentially affected, and of course it's an important benefit, because if people don't receive this benefit when they should, they're disenfranchised. So here's the formula. For each jurisdiction and for each language, you've got to compute a set of statistics about the jurisdiction, and they have to do with voting age citizens in the jurisdiction that speak a given language, L, and then you've got to figure out the fraction of those that are limited English proficient, and then you've got to compute the fraction of those that it's like an illiteracy condition, that have less than a 5th grade education. You take those statistics, you divide two of them. This is basically a threshold on the limited English proficient. It's either like an absolute threshold you can satisfy it by, or a kind of multiplicative threshold, or ratio of your population that's voting age citizens. And then you also have to satisfy this little threshold. This is a constant that they decide, which has to do with the overall US illiteracy rate, national illiteracy rate. Okay, so then if you satisfy this little Boolean condition, then you're covered. All right, so it's a Boolean thing. You're either covered or you're not covered. Each jurisdiction, each language. Okay, so here's what we did. We took the public use data, okay, and treated it as ground truth. All right, it's not ground truth. It's got actually a lot of disclosure limitation stuff in it, and who knows what they do to it, other than John. One language, which is Hispanic, which I know is not really a language, but to the Census Bureau, that's a language category, and it's actually one of the most frequent ones. So in that sense, the counts are higher. And the true positives here is 175 positively classified jurisdictions in the data that we considered ground truth. And here's what you find if you look at this. So then what we measured was correct classification rate for the covered jurisdictions. All right, so those are the true positives. We just looked at, of that set of 175, how often are they going to be correctly classified as covered, as they deserve to be? All right, so here's the good news. The good news is that there's some that, and even a lot, at epsilon 10, a lot of them are correctly classified all the time. But the problem is that as epsilon goes down, you see that there are quite a few that have very low correct classification rates. So at epsilon 10, we might be happy that the lowest correct classification rate's 95%, but at lower epsilons, we would probably be unhappy. Now, you can run this experiment again, comparing two mechanisms where one gives lower total error. Actually, DAWA and Laplace on this task give about the same total error at epsilon 0.1, and DAWA starts to outperform Laplace at an even lower epsilon. And this graph is showing that the disparities, you get lower overall error, but again, you get disparities that are much more severe. In fact, you see people who are, I think due to just the bias in the counts that DAWA is creating, never going to be classified correctly for any run of the algorithm.
So this is a point where I need to insert a footnote. Is that okay?
Okay, yeah.
Instead of rank, population is what, it's ranked on population, right?
No, this is actually just ranked on the correct classification rate. So we had 175 jurisdictions. Yeah.
That's very positively correlated with the population in the voting district. And in the smaller population voting districts, we published the sampling error for the statistic that the determination was made on. They have a similar property, but it's not challengeable. So So I'm not worried about you doing this simulation, but you ought to do that simulation too.
So if I understand what you're saying, you said we should consider how many people are disenfranchised, not just, like these districts might be very small populations. What?
I guarantee you that they are.
Okay, okay.
Well, maybe the point that I thought John was making, which is related to that, is that if you look at sampling error, it's going to exhibit a similar feature that the small districts or districts with small populations of the covered type are going to have. You're going to get a lot of, if you were to hypothetically resample, you would sort of very often make different decisions.
Yeah.
Much more so than with the big.
Okay. So and what do you draw from that? I mean,
If you're going to get a line like that, it would be interesting to see what 2 epsilons it sits between.
Yeah. What you get
just from the sampling.
is this, the noise added for confidentiality is not necessarily creating a problem here. That
Okay,
wasn't-
so you would want to compare. Okay, let me just rephrase. You want to compare this rate of misclassification to what is sort of inherent in the data from sampling.
For example, yeah.
Okay. Yeah.
Slightly different question. It's fascinating. But you use the phrase, correctly classified, something like correctly classified as they deserve to be.
Yeah. Right. Okay.
Which is sort of as if these thresholds in this formula are somehow, important to the policy goal, that it matters that it's 10,000 and not 9,000, or.
Yeah.
And so I wonder if there's something else to look at and measure that maybe kind of gets at, for example, the number of speakers of that language that don't, that do or don't get a ballot in their language.
Yeah. Well, I think that's a totally valid point. I mean, we asked ourselves also, like, why does this formula exist, and what does it really mean? What is it trying to capture? I don't know. I never got a good answer to that, but.
Political compromise between guaranteeing that there would be Spanish ballots and allowing for the possibility that there would be ballots in one of approximately 50 native languages that have diminishingly small numbers of speakers, but which might constitute the majority or the over the threshold in these specialized voting districts. That's the compromise.
Okay. I don't know if that helps, Alil, but I mean, obviously, the other issue is that mistakes in one direction seem much more costly than others, and so we probably shouldn't be doing this raw application of the formula to noisy data. But as I said, it's not so easy to move to another approach.
If you do this with the direct estimates of those, which is one of the simulations you should do, I predict that you will get a picture that's worse than your red line. But it will be, because so many of them are noisy based on sampling. The modeling was designed to pool the data from large numbers of similar districts, so you can get a better estimate of where you want to put the line, but it still can't get rid of the variability that's due to sampling.
Yeah. Okay. Yeah, Ian.
You're going to get a flip of this. You must have a bunch of districts that are small that get kind of incorrectly classified in the other direction.
Yeah,
but
for sure.
as John's pointing out, those are
Probably far more, but presumably the cost there.
In some sense treated, but aren't because of the sampling variability.
Yeah. 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 Okay. Well. Okay. Let me try to go. I'm almost done, and I'm almost out of time. But we also studied a funding allocation problem called Title I, where there's a total allocation for school funds. They're allocated to school districts in proportion to essentially the number of eligible students in the district, moderated slightly by the average student expenditure in that district, just because things are more expensive in some areas than others, and so they adjust for that. We treated this as true because there's a lot of public information about average student per student expenditure, and so here the effects I think are a little less dramatic, but still you see that because of rounding, small districts tend to get a positive bias and get over allocated, and that it's compensated for by the larger districts. So what we're plotting here is a sort of multiplicative error. This is the magnitude of the true allocation, and on a log scale, the multiplicative, the ratio of the error. Okay, so the one interpretation of this is that the large districts tend to get a small tax in order to compensate for the positive bias on the small districts. Okay, so I'll just wrap up and we can continue the discussion. I think it's the case, I think I've shown, that assignee populations do not bear the utility cost of our common privacy mechanisms equally, and that there's a somewhat complicated variety of causes for this. Including the things I've talked about. When I say those who get asked about less often, what I mean is that when we do the workload optimization, it's the sort of queries that don't appear so often in your workload, or the parts of the domain that people don't ask about so much, that the optimization can tolerate like letting the noise go up. And so, there's other examples. I gave this state hierarchy, but you could look at like when we optimize the SF1 persons queries, and you look at the distribution of error across age groups, you find some weird effects where very old people have very high error and vote, and there's like a step down when you look at children versus like voting age, and there's some other weird effects. And we could adjust, we can adjust for those effects, and that's sort of part of the point. I guess as next steps, I'll say for what epsilons are these disparities small enough to ignore? And then I guess the big question or the big response that's emerged here is that, these effects exist in the data because of sampling, and therefore we should see how the magnitude of the effects, how they compare to those. Maybe also, I also think it's interesting, the extent to which does that mean they could compensate for each other, or it's not as bad, or we shouldn't blame the privacy mechanism? I'm not sure what the conclusion is. I think we can change our privacy mechanisms to address some of these. For example, a very concrete thing for us to implement in the context of the matrix mechanism is another optimization objective that that targets accuracy disparities, and I think we can do that, and we're looking at that. It's obviously interesting to look at post-processing or more sophisticated assignment methods that take into account the noise if you can analyze the noise. But there's questions about whether this is palatable from the standpoint of regulation. And then I would perhaps ask if you were a resident of some of these jurisdictions and you were going to be disadvantaged by by the privacy mechanism, or at least in part because of the privacy mechanism, would you still choose to have your privacy protected at the same level, or might you want to choose, if you were able to have less privacy and more accuracy?
Or maybe just allocate more money overall.
Okay, I'll end with this and thank my collaborators, and all the simulations were run in our system Ectolo, so students, if your advisors want to reproduce these results, point them there.